The next design method we're going to look at is called the permissible velocity method. If you have not done so already, download the following reference from M. Hanif Choudhury, 2008, Open Channel Flow. This is available to you at no cost online. The permissible velocity method is described on pages 286 to 289. The concept for the method is that channel banks will be stable and will not erode until a threshold average velocity is reached. To use the method, the required information is the soil type, the ground slope, or the slope of the bottom of the channel if it's significantly different from the ground slope, the channel sinuosity, the recommended side slopes, the recommended maximum velocities, and the recommended end values. Here is the example. An irrigation canal will be constructed in a silty clay soil with a bottom slope of 0.005. The flow rate will be 100 cubic feet per second. The channel will have a moderate sinuosity. Determine the dimensions of a trapezoidal channel that will have stable banks and be able to carry the flow rate. So utilizing the reference that was noted previously, Table 9.2 says that the side slope would be 2 to 1. Table 9.3 says that the permissible velocity would be equal to 1.1 meters per second. Because the channel is sinuous, and then there will be some additional stresses on the bends, the permissible velocity is reduced by a factor based on the sinuosity. So for a moderate sinuosity, on page 286, the velocity reduction is 0.13. The calculations would proceed as we normally do by writing down what we know and assigning those to the variables that we use repeatedly. So you'll notice we have the variables which we've been using up to this point, and then there's a sinuosity reduction factor which I just happen to call sin equals 0.13. So first we would convert the velocity of the metric units into the velocity in US units. So we would use a conversion factor between meters and feet. Then we would reduce the allowable velocity based on the sinuosity factor. We would then compute the area as the flow rate divided by the allowable velocity. Once we have that, we would compute the hydraulic radius. Knowing that the hydraulic radius is the area divided by the wetted perimeter, we can then solve for the normal depth and the bottom width of the trapezoidal channel. This is obviously from a lingo file, and it shows a list of all of the knowns. The implementation in the lingo file of these equations is shown on this slide. So there's the conversion, allowable velocity, the area, hydraulic radius, and then you can see the wetted perimeter is the area divided by the hydraulic radius, and then you can get the normal depth and the wetted perimeter in this equation, which would then give you the solution of the normal depth and the bottom width. The answer to the example are shown on this slide, and you will be provided with the permissible velocity method instructor for this particular example. So the answers, the allowable, with no sinuosity correction, the allowable US velocity would be 3.61, When you correct it for the sinuosity, the allowable is 3.14, and then you can see you get a bottom width of 24.47 and a normal depth of 1.19 feet.